All right, open up your book to section 6-5. We're on page 307 in your book. The title of this section is Circular Functions, and the objective is to learn about the circular functions and their relationship to our trig functions. Let's start out with a bit of a problem that we're kind of running up against right now. And here's the problem. All the trig functions that we've worked with so far are trig functions that are defined in terms of some angle. It doesn't matter whether you're talking about an angle that's in a right triangle or an angle that's been put in standard position in the coordinate plane. They're all dealing with the sine, cosine, tangent, or whatever trig function it is of some angle. The argument that you're providing, the input that you're providing is some angle. Well, what happens if I want to extend using these trig functions beyond working with just angles? I run into a bit of a problem because all these are defined in terms of some angle. This is the issue we're dealing with here. What if we need a periodic function with an argument other than an angle to model some data? Maybe you're trying to measure annual temperatures. You have a high temperature and a low temperature throughout the year, and it would be somewhat cyclical. After one full year, I expect those to start repeating. But the input is not going to be an angle. It's going to be a day number or something like that. What if I'm trying to model annual rainfall? Again, you have highs and lows throughout the year. I would expect that to be cyclical. I would expect to see that every year it starts to repeat. But again, the input is not an angle. Daily tides, again, the input is not an angle. I have a high tide, a low tide, a high tide, it goes on and on throughout the day and throughout the week. What if I want to model those using a periodic function, but I don't want to be tied to working with only angles? Well, what we learned here in the last section is that a radian measure is defined as an arc length divided by a radius, which this equivalency then gives me a way to convert from being a radian measure of some angle there on the left to a ratio of an arc length over a radius over there on the right, which is kind of the first step that I need to try to get away from being forced to working with just angles with my trig functions. And even better yet, if we were to talk about the unit circle, remember, is defined as a circle whose center is at the origin, whose radius is 1. If your radius is 1, then when you calculate the arc length divided by the radius, that would be the arc length divided by 1, or that's just the arc length. And now I could say that for the unit circle, that the radian measure and the arc length are the exact same. As you can see over there in that sketch, if I've got some angle marked as x radians, that corresponds to, on the unit circle, some arc length of x units. And now I'm no longer tied to this angle measurement. I can now think of this as being some distance here, which allows me then to get away from just being forced to work with angles now. This is what we're trying to do. So let's define what a circular function is. Let's define some point UV that's going to be on our unit circle. It'll be the terminal point of an arc of length x in standard position on that unit circle. So I'm no longer talking about the terminal side of an angle, but rather I'm talking about a terminal point that falls on that unit circle. It's the terminal point of an arc on that unit circle. Then your 6 circular functions are defined as follows, if that's the case. Let's take a look at a unit circle here. with a radius of 1, and our r value is equal to 1, which means that the sine of x would be equal to v over r. We know that's its definition, but since r is 1, that means sine of x would just be equal to v. Cosine of x would be equal to u over r, but again, since r is 1, that's just u. Tangent of x is equal to v over u, since it's the ratio of sine over cosine. That's a quotient property we learned earlier in this chapter. In fact, we know the reciprocal and the other quotient properties there, so cosecant of x would be 1 over v. Secant of x would be 1 over u, and cotangent of x would be u over v. This is our definition of what it means to be a circular function. Notice that we're defining a point uv that's a terminal point on some arc that's on the unit circle. We're not tying it to a terminal side of an angle. We're getting rid of this idea of having to stick to working with just angles, but rather we're measuring this angle, or this arc length x in this sketch. A couple things to note here about your periodic circular functions. These are really working in radians then. And so we know that sine and cosine had a period of 360 degrees. We know that 2 pi is equal to 360 degrees, so we should understand that means that the period of these circular functions was going to be 2 pi radians. Turns out that secant and cosecant have the same period. And it turns out that tangent and cotangent have a period of pi. And again, when we looked at the sketch of those functions in degrees, if we understand the relationship between degrees and radians there, we should understand that those must have a period of pi units. And in fact, the really good news for us is that circular functions are equivalent to the trig functions that we already know and have been using, but we're working in radians on the unit circle. So a circular function is just a special case of a trig function whose angle is in radians, so we're working with a arc length then instead, or I can think of it that way, and it's on a unit circle. All right, so where have we started and where are we at this point in terms of our work with our trig functions? When you walked in this year, I'm sure you understood SOHCAHTOA. That is, you understand the relationships between sine, cosine, and tangent and the three sides of a right triangle. So you understood the ideas of working with angles of right triangles for acute angles. That we were pretty good at. We wanted to extend that. That's one of the first things we learned then in the previous chapter was how do I extend this to working with any angle? So that's what the second thing there is. We've worked with points in the coordinate plane so that we can now define a point in any quadrant and thus an angle of any size. So we jumped outside of just working with angles in a right triangle. And now where we've taken this to is we're now talking about circular functions for values other than angles. So I might be using inputs that are not actually measuring angles anymore, and I'm still using those same trig functions to do it. One last thing here to note before we look at a couple of examples, because we now have trig functions that are going to be defined in radians, some that will be defined in terms of degrees. We've talked about the importance of indicating that degree mark. That indicates degrees. Without it, it indicates radians. Well, here's the other notation that we're going to use. If you're given a problem and it's defined in terms of Greek letters like theta or alpha or beta, anything sort of a Greek letter like that, that will be measured in degrees. Without the problem having to say it, it'll be measured in degrees. On the other hand, if it's using Roman letters like X or Y or whatever it might be, A or B? Those are radians. All right, probably theta and x are the two most common ones. And just realize that they won't have to tell you that it's in radians or that it's in degrees. Once they tell you the variable, it's going to be understood that these are the units we're working in. So theta is in degrees, x is in radians. All right, so let's take a look at a couple of examples. Example number 1 there on page 309 says to plot the graph of y equals 4 cosine of 5x on your grapher in radian mode and find the period graphically and algebraically, and then compare your results. Well, they told you what to graph this in radian mode, but as we just said, since they said that this was y equals, let's write down the equation, y equals 4 times the cosine of 5x. Since it's in terms of x, that automatically tells you that this is in radians. If it had been a 5 theta, it's in degrees. All right, so let's think about what the sketch of this is going to look like. I know what the graph of cosine looks like, and I just got to think about what the 4 does and what the 5 does. And if I think of my general sinusoidal equation, that probably helps me out a little bit here. The 4, remember, is your amplitude. So the amplitude is 4. So that means that it's also a vertical dilation, right? You've stretched it 4 units in the vertical direction. And the 5, that's a horizontal dilation factor there, and that means 5 is actually affecting our period. So the period of this thing, now because this is in radians, instead of being 360 degrees divided by the absolute value of b, it's going to be 2 pi. We're converting over to radians for this. So 2 pi divided by the absolute value of 5. I guess I can write it that way. Of course, the absolute value of 5 is just 5, so this is 2 pi over 5 is the period of this function. With that, I should be able to sketch this. I know what cosine looks like, so I've just stretched this thing in these two directions here, so I should be able to sketch it and mark those things on my graph. So if I just sketch a standard cosine function, which kind of looks something like this, this of course is at 0, and since the period of this thing is 2 pi over 5, that means that this must be at 2 pi over 5, because the period tells me how far it is from this high point to the next high point, right? That has to be 2 pi over 5. And furthermore, I know where it crosses the y-axis at. Since I've stretched it vertically by a factor of 4, instead of being at 1, it should be up here at 4, and that's the upper bound for this. And that means that the lower bound, although not quite to scale here, I guess, this would be at -4. That should be a pretty good sketch of this thing, but let's grab our calculator and see if, in fact, that's what we get. All right, so with our calculator, let's punch in y1 as our function that they gave us there. And the function was 4 cosine of 5x. And again, we're in radian mode, so make sure that's the mode you're in there. Go to your mode menu and make sure that's where you're at. And for our window, we're going to set it to the window so we see one full period of this thing. So we should go from 0 to 2 pi over 5 is what we claimed was one full period of this thing. 2 pi divided by b should give us the period. And a scale here, I guess if you want to break that up a little bit more, you can. You could put this in multiples of 2 pi over 5, I guess, if you want to do it that way. I'm going to just leave that as 1. Actually, maybe I'll write it as 2 pi over 10. It'll be halfway through. I'll see a tick mark. And then for our y's, probably -5 to 5 will be fine. If you want to go exactly to fill your screen, maybe that's what I should do. Go from -4 to 4. That was the amplitude of this thing, so we'll do that. And if we hit graph, we should see one full cycle of this function. That's, in fact, what we got there. There we go. All right, and they said find the period graphically and algebraically. Now, we didn't do it graphically, but if you trace your graph there and use the maximum feature to find out where your high point is at, you'll find that that is 2 pi over 5. We already did it algebraically. All right, let's take a look at example number 2. Example 2 there says, find the particular equation of the sinusoid graph. Notice that the horizontal axis is labeled x, not theta. Again, that's the hint here. Are we in degree mode or radian mode? It's x. That x there is going to tell me that this must be radians here. Okay. And it says, indicating the angle is measured in radians. They told us that, but again, from this point forward, you shouldn't expect that they're going to tell you that. You got to analyze that and see that for yourself. Confirm your answer by plotting the equation in your graph. Okay, so let's find the equation of this thing. First thing I guess to do is to mark our upper bound and lower bound. So they've marked, actually they did mark the lower bound. That's at 1, right? And then we got 2, 3, 4, 5 is the upper bound here, it looks like. So that's 5. So we can find the sinusoidal axis. That's the line that goes right through the middle of this thing, right? That should be right here at y equals 3. So that's our sinusoidal axis. And then for your phase displacement, looks like we have our high point right here at 1. And then it looks like the next high point actually is at, careful with that, it looks like it's 11. They marked 10 there, but I think they were just, I'm not sure why they marked 10, to be honest with you. That looks a little misleading for them to do that. But anyway, 11 is actually the location of the high point there. Maybe they're just trying to mark increments of 10. I'm not sure why they did that. So I can measure then the distance between those. That's my period. So the period is equal to 10, right? 11 minus 1. All right, so we should be able to come up with our equation then. And again, we're doing this in radians. So y is equal to, our sinusoidal axis is 3. Amplitude from 3 to 5, that's 2 units, times the cosine of, now we're doing this in radians, so instead of 360 over the period, it's 2 pi divided by our period, which we said was 10. And I like leaving it in that form. You could reduce that. But when you write it in this form right here, then it's 2 pi divided by some number. The number you're dividing by is the period. That's why it's nice to leave it in that form. But certainly if you reduced it, that'd be fine. And then times, and then since this is in terms of x, it's radians, that's what my variable needs to be. Make sure you use the right variable. You write down theta, and it's going to be wrong. Write down x, it's correct. And minus, our phase displacement we said was going to be 1. So there we go. There's our equation. They want us to come up with that equation. I think they said to graph this as well, or to plot it to confirm that. So we can do that. So grab your calculator and let's confirm that. All right. So on your calculator, let's go to your y equals menu. Let's get rid of that function from example 1, and let's plug in our new function here. 3 plus 2 times the cosine of 2 pi over 10. Times x minus 1. And for our window, again, I'm going to just set my window so I see one full period of this thing. So we're going to start out at 1 and go up to 11. Period is 10. And a scale of 1 will be fine. And then for our y values, it was the lower bound was 1 and the upper bound was 5 is what the sketch showed us there. So when I graph this, we should see one full period of this function. Just grab a picture of that. All right, there we go. We've got ourselves a nice little sketch of what that function should look like. That definitely looks like the right graph there. All right, let's take a look at one last example. Example 3 on page 310. It says to sketch the graph of y equals the tangent of pi over 6x. All right, so we have to go back and kind of remember what the graph of tangent looks like. We went through and looked at each of those additional 4 trig functions. We already had seen sine and cosine prior to this chapter, but now we've seen the graphs of the other 4 trig functions. So remember what the tangent function looks like, and we're going to do a little bit of a dilation, I guess, is what we're going to do, a horizontal dilation of this. So y is equal to the tangent of pi over 6x. Okay. Now when you see the pi over 6x, you should be thinking about what the period of this function is and then how that pi over 6 is affecting this. Remember that your period of your tangent functions, the period is pi. So if you think about what the value of b represents, the period is going to be equal to, instead of 2 pi, it's pi divided by the absolute value of b. Or in other words, if you solve this for b, the absolute value of b is equal to pi divided by your period. So in other words, having this in the form of pi over 6, that's actually pretty nice, because in that form there, that's what the value of b is. It's this guy right here that we're talking about. It's in the form of pi over some number, so that number that we're dividing by must be the period. So that tells me the period must be 6. You can actually evaluate that first equation up above there and see that. If the period is equal to pi over b, and b is pi over 6, solve that, you'll find out period equals 6. Okay, but again, if you leave it in this form here where it's pi divided by some number, it makes it really easy to come up with that. All right, so let's sketch what this looks like. The tangent function, that's the one that has a bunch of vertical asymptotes. So it's got vertical asymptotes here and here. It actually crosses through the origin. We'll try to put these vertical asymptotes equally spaced apart, approximately in the right spots, somewhere about right here. And the tangent function starts down here. I'm going to go through the origin for the first one here, but it starts in the down on the left side of each subinterval and then ends at the right side going up. It's an increasing function, so it does something like this. I guess I could have just started on the left side and worked my way to the right, but anyways, there we go. There's what tangent looks like. Now for the tangent of pi over 6x, all you've done is stretch this thing horizontally, is really what we've done. And so the question is, well, where are we crossing the x-axis at, and where are our vertical asymptotes? So instead of having vertical asymptotes at pi over 2 and negative pi over 2, it now turns out those are going to be at 3 and negative 3. And how do we know that? Well, I need to have this distance between these. The period we said is equal to 6. And the vertical asymptotes are, I should say, the tangent functions centered through the y-axis there. So it has to be at negative 3 and 3 in order for that interval width to be 6. So if that's a vertical asymptote at 3, 6 units later would be at 9. Before that, that would be a negative 9. And if you want to mark where we cross the x-axis at, I'll put that in a different color at, it's halfway between these, right? Negative 9 to negative 3, that's a negative 6. This one, of course, is at 0. This one, of course, is at 6. There we go. There's our sketch of our tangent of pi over 6 times x. And you can grab your calculator and verify that, in fact, that is the case. Let's go ahead and do that. So in y equals, let's put in tangent of pi over 6x. And again, I'm just going to look at one full period of this. So we said from negative 3 to positive 3, we should see vertical asymptotes on our graph there at each of those values. And probably if we go from like negative, well, let's go negative, negative 10 to 10. Let's try that. If we graph it, there we go. That's one full period of this. Doesn't look all that interesting. Maybe to see a few more periods would actually be a little bit more helpful. Let's go from negative 9 to positive 9, so we'll get 3 periods of this. Yeah, that looks pretty good, actually. I'm going to grab a picture of that because that looks closer to what we sketched. All right, very nice. That right there is the end of section 6-5.